Okay, so where's everyone? Okay, so a couple of quick announcements. There's going to be it's called the course feedback email pretty soon. I think by next Monday you should get it, Monday or Tuesday morning. So it'll be very useful if you can give feedback. Basically, I think this is the first time we tried having local compute resources. So things like that, based on the feedback can happen. So give some feedback about such things. Second thing is you do have a project submission, right? So most of the teams have talked to me. So try to don't be too ambitious. It's more important to have a clean creative work, completed creative work, than to have parts that are not working, right? So try to be less ambitious in the sense of at least get some baselines, some simple things working first. Okay. Okay, so let's come back to the topic. I don't know where the others are, but so next, what we're going to do in terms of the next 50 minutes is we're going to look at 3 more algorithms. Okay, Thompson sampling, Exp3, and Exp4. Okay, so the 3 algorithms. There is, of course, there's a reason why I'm introducing all 3. So let's look at Thompson sampling. It's a so it's also to solve the Bandit problem, okay, which means that try to learn while earn, as in minimize regret, cumulative regret. The algorithm is Bayesian in nature, okay, so that's a key part, and it was proposed almost 100 years ago in 1933, and was analyzed recently. Actually, there were several analyses of this work. So what is the idea? The idea is you don't know what's the conversion rate for each of the option. Okay, so you have 5 websites. That's a running example. So you don't know the conversion rates for each of the options. So what you assume is a uniform prior. I don't know the conversion rate. Let's say it's between 0 to 1 normalized. So I'll assume a uniform distribution first. That the conversion rate can be anything between 0 to 1. Okay, so that's the uniform prior. Okay, on the parameters on mu's. Okay, so now mu's are random variables, so you assume a uniform prior on them, and then you start maintaining a posterior distribution. So uniform prior. So remember, in base rule, you go from a prior to a posterior. Why do you go from a prior to a posterior? You get some evidence, and therefore you can update your belief. In this online learning setting, in this Bandit setting, you get feedback every round. So every time you try an arm, you get a feedback. So based on the feedback, you can get a new posterior. So you go from prior to posterior, 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 posterior only if you get some evidence about that arm. Okay. So you maintain a posterior pi I of t. I represents the arm, ith arm, and t represents the round, and that's a belief on the mean reward, belief on mu I. Okay, the mean reward for that arm. Okay, and then so you have a prior, you're maintaining posteriors based on the data. Okay, and then how do you take decisions? Okay, so that's also pretty interesting. Is that you sample a number from the posterior. So the posterior number is going to be the posterior is going to be again let's say you are uniform between 0 to 1 as a prior. Your posteriors will be, if your observation, if a likelihood model is Bernoulli, your posterior will be what is called a beta distribution. I'm going to talk about it in the next couple of slides as well. It's a distribution between 0 to 1. You get a sample. It's going to be a number between 0 to 1, right? So you get one number per arm, a sample. Okay, one number per arm, 5 arms, 5 numbers. Then you compare which number is the highest, and that's the arm you're going to play. Okay, so that's it's a slightly different way of picking an arm versus what we saw in the previous 2 algorithms, epsilon greedy and UCB. Okay, and that's the arm you're going to play, and that arm index is I'm just representing as IT. Okay. Any questions about the procedure of the algorithm? What is it? How do you sample?
How do you get sample?
How do you sample from a posterior? We discussed this. Yeah.
No, so in a multi-arm bandit, you get a sample. You won't get sample unless you put the arm.
No, it's not a sample. So you maintain whatever belief, right? So whether it's a prior or posterior, if you tried that arm, you'll get evidence. Okay, that's you can think of that as sample from the reward, but for us it doesn't matter because it's exogenous. Like we get some number which is a feedback on how well that arm did. This sample is actually, once I get that evidence, I'm going to update my posterior. It's just Bayes rule. Okay, Bayes rule may involve all that inference stuff that we talked about a couple of weeks ago. Once you have the posterior, from posterior I want to sample a number from each posterior. So there's a posterior that I'm maintaining for each arm. I'm sampling a number. I get 5 numbers in the 5 arm case, and then one of the numbers is going to be the highest, and pull that arm. Okay, that's on a different sampling. Okay. So what I mentioned about like uniform distribution and beta distribution, I'm gonna I don't know if we need conjugate properties here. So okay, let's see. Okay. So actually what I'm going to do is skip the conjugate priors business. It's a lot of slides. Okay, so actually let me just use so there were 5 slides that I kind of flipped over, but I'm just going to explain it in using the board. Okay, so if you're so here's the concept of conjugacy. So in general, I was supposed to maintain pi I of t. I was supposed to go for, so from pi I minus 1, so pi I of t minus 1, so whatever posterior I had before, if I had pulled, if I pulled it is equal to I, in this round, in this interaction, I did try the arm I, then I'll get some evidence, right? Some, whether they clicked or not, right? Clicked or not, some observation, reward, right? In this round, right? So let's say this is 1 or 0. Okay, Bernoulli, right? Remember there was a Bernoulli process, a Bernoulli distribution. So given this reward, I want to go from this posterior to the next posterior, right? That's what I want to do, right? So at the beginning of time, just think of the posterior being the prior itself, some uniform distribution. Okay. So actually, one fact, uniform between 0 to 1 is the same as what is it, beta 1 1 or beta 1 half 1 half? Who knows this? Okay, doesn't matter. Let's say 1 1. Okay, if it's 1 half, we'll figure it out. Actually, it's 1 1. Okay, this is fine. So uniform distribution is a parametric distribution. Okay, it's a continuous distribution on 0 1. So if you want to really plot the diagram, it's like this, right? This is the probability mass function 0 to 1, right? That's uniform. You get a sample, it can be any number with same probability. Beta 1 1 is the same as uniform distribution, by the way. Beta distribution is also parametric distribution, has 2 parameters, first argument and the second argument. If you set the first 2 arguments to be 1 and 1, then it's also uniform. It's the same, it looks the same support, everything. Okay. In general, the parameters are alpha and beta. Okay. This is a recap for some of you. Some of you must have seen this, but nobody has seen conjugacy before? Okay, so anyway, what is so this was just naming of some distributions. What we care about is this is our goal, right? And in general, how do you do this? You actually just use Bayes rule. So pi I of t is proportional to the likelihood of observing this reward, right, times the previous belief, which is going to be the previous distribution. Okay, this is Bayes rule. I mean proportionality because there's going to be divided by the probability of observing just R. Okay, which is just sum over all the. So I'm not explicitly writing this pi here because I want to actually do it in the next minute, which is think of this pi as a beta distribution. Okay, so remember I wanted to maintain a belief over the mean reward. Let's say the mean reward is a number between 0 to 1. So initially my prior is going to be uniform, so that's why I said beta 1 1. Okay, in the next round, let's say I did pull that arm. Okay, let's say we're only discussing about arm I. I is some fixed first arm. Let's say we had a uniform distribution. We tried that arm. We got some reward. Reward was 0. Did not click. Then I have to update, right? I have to do base update. So my pi I t minus 1 is uniform and essentially beta distribution. My new distribution posterior, okay, could be any distribution, right? It just depends on this formula, base rule, likelihood times prior divided by the sum over likelihood times prior. Okay, that's whatever base rule is. Now it turns out that if the likelihood is Bernoulli, okay, and the prior is beta, okay, then the posterior is also beta. You don't have to do any integration, any summation, anything like that to get this. Okay, so that's called conjugacy. So beta is the conjugate prior to the Bernoulli likelihood model. Okay, so that's what I want to. So forget about all this online learning for now. So here, all I'm saying is if you had a beta distribution. So what is this beta distribution? It's just saying mu I is beta. Let's call it alpha old and beta old. Okay. Then I get a reward according to. Then I observe a reward. So let's. Okay. Bernoulli. Okay. Bernoulli with mu I. Okay. Then my posterior distribution probability of mu I given evidence, which is that reward, maybe the reward is 0, is the probability of a reward given mu I times probability of mu I itself, which was, this was what I was saying was beta, right? Alpha old and beta old. Whatever that parametric representation is, let's not worry about how the form looks like. Just like exponential distribution has some messy PDF function, here also there will be some function, doesn't matter. Okay. This one we said was Bernoulli. Okay, given mu I, r is equal to 0 or 1, we know what it is. What is the probability? Probability of r is equal to 0 is 1 minus mu I. Probability of r is equal to 1 is mu I. That's very simple, right? And this divided by, probability of r is equal to whatever. So let's say we observed actually 0, right? So probability of r is equal to 0. That's base rule for you, right? So all I'm saying is, if this is beta, then it turns out that if you multiply beta with a Bernoulli and do the division, turns out this is also beta, okay, with some alpha nu and beta nu, okay, which means that you don't have to actually, when you say I maintain a posterior, I don't have to actually maintain any distribution. I just have to maintain two numbers, because those two numbers are parameterizing the distribution. So think of, instead of maintaining a Gaussian bell curve, I can just maintain the mean and the standard deviation. That completely determines the Gaussian, right? So here I'm saying that because of conjugacy just means is a nice thing about Bernoulli and beta, special properties, so that if I do base rule where Bernoulli is the likelihood model and beta is the prior, then I get a beta back. So I don't have to do any integration to get the posterior. I can just maintain these numbers, and in fact alpha nu is going to be alpha old and beta nu is going to be beta old plus 1, okay, because r is equal to 0. So if r was 0, beta is increased by 1, and if r was 1, alpha would be increased by 1. Okay, very simple update rule. Okay, so this is called conjugacy, and it makes the life easy in the Thompson sampling algorithm, because you are supposed to maintain posteriors and update the posteriors. If the posterior distribution is very messy, instead of beta you maintain some very mixture of Gaussians. Updating the mixture of Gaussians depends on the likelihood. The likelihood function could be very messy. Then you really have to do that inference. Okay, you really have to do base rule and compute all these things, all these terms. Okay, that's all. So those were the slides. So I skipped them. Okay, all these. So here, think of categorical as an extension of Bernoulli. Remember, if Bernoulli is just 2 outcomes, categorical is like 10 outcomes. Remember the lambda stuff that you're talking about in Gibbs sampling. That lambda, if k is 10, it's a categorical distribution. Okay, if it was 2, then it would have been a Bernoulli type of a distribution. And Dirichlet is an extension of beta distribution. Okay, beta is just has 2 parameters, but Dirichlet has k parameters. Okay, just a k dimensional extension of beta Bernoulli that I discussed. Okay. Anyway, any questions about Thompson sampling though? That conjugacy was a tangent to make, it was just a comment about the computational issue of the algorithm, but the algorithm is very simple. Maintain beliefs, update the beliefs if you get information. Once you update the beliefs, sample from the beliefs and pick the largest number and play that arm. Okay. How is this helping exploration? If you're not updating a belief is spread out, and so if beliefs are spread out, you may sample a high number. Okay. If you're not trying that arm enough, just like in the UCB case, if you're not trying that action enough, the bonus term is gonna become higher. Okay, relatively speaking, and so you'll try that just to see whether it still is a low reward arm or not. That's all. Okay, and next let's go to a different slightly different setting. So far epsilon greedy, UCB, and Thompson sampling, we've been thinking about each action has some stochastic reward process, like a Bernoulli. So if I show this website, the user is going to flip a coin and click convert or not convert. Okay, that's a little bit unrealistic. Okay, so what we're going to do next is look at an example algorithm or look at a setting where we can drop that assumption. So we don't have to assume anything about the reward. Reward can be any number between 0 to 1, let's say. Okay, bounded. But we are gonna ignore, so we're gonna not assume that there is a stochastic, there's a distribution there. Okay. Then so basically we can draw the probabilistic reward assumption. Then even the definition of regret becomes a little bit murky, right? So what is expected regret? There is no expectation there, right? Because things are not random. There is no mu star, there's no mu I. Okay. That's one issue. Okay, and the other issue is if there's no randomness, then what statistics will I keep and how will I actually minimize my regret? Okay, whatever that new regret definition would be. Okay, so we'll address these two things. Okay, but what would be the template setting? It would be a template as in like how would the setup look like? It will be pretty much the same as before, except for this point. So in each round, player selects an action and player observes a reward. Okay, so xt of action that I took is the reward. Okay, because we dropped the probabilistic aspects, we're going to concoct that there's going to be some other guy, okay, who's actually giving me rewards. It may be another human, okay, not a stochastic, no distributions anymore. It could be a human. Okay, we're going to call them adversary. Okay, because they are going to make us get less money over rounds. Okay, so they're going to try to be bad to us. They're going to minimize our earnings, and so we'll have more regret. Okay, that's what they're going to do. So the way they're going to act is they're going to in round T, they're going to just pre-decide some numbers for each of the 5 arms, each of the arms. Okay, some numbers like whatever is the reward number, like 0.3, 0.5, 0.8, something. They'll decide them before. And I play some arm and I just observe one of the entries which I actually played. Okay, that's called that's called bandit feedback. Okay, there's other problems where you actually observe the full vector that the adversary chose, but we are not looking at the setting. Okay, we're looking at this setting. Okay, where adversary chooses all the numbers, 5 numbers. I pick one of the arms. I see the number. Okay, so that's the workflow. And in this workflow, I didn't tell you so there were 2 things, right? One was what was the reward, what was the regret definition. The regret is going to be almost the same. It's going to be the sum of rewards that you got, xt of it, okay, minus the sum of rewards that you could get from a single best action in hindsight. Okay, which means that I'm going to look at max over I. Okay, all I'm saying is adversary is picking numbers, right? So think of it like this. So adversary, let's say there are 2 arms, arm 1 and arm 2. So arm 1 and arm 2. and the adversary picks numbers, okay, 0.3, 0.5, 0.4, 0.6, 0.9, 0.2, okay. Adversary is picking a bunch of numbers, okay, 3 rounds in this case. What we'll do is figure out, okay, if I pulled arm 1 all the time, then what is the total regret I get? Sum of these 3 numbers, right? If I always pulled arm 1, I will get these 3 numbers. If I've always pulled arm 2, I'll get some of these 3 numbers, okay. 0.16, sorry, 1.6, 1.6, and how much is this? 1.3, right? So if I know these numbers, I would have pulled arm 1 because that has the highest total reward, okay. So this 1.6 number is this a first number, okay. That's in hindsight I would have picked the first arm and therefore achieve 1.6 as my total reward, okay, total clicks or sales or whatever it is. But I actually picked a bunch of arms which are IT, okay. In every round, whatever arms I picked, maybe in the first round I picked the first arm, maybe in the second round I picked arm 2, maybe in the third round I picked arm 3, okay. Then there will be some number of rewards. Then those are rewards I get, 0.3 plus 0.6 plus 0.9, okay. We're just comparing the number that you would have gotten for a single best guy minus the numbers that you got, okay. In this case, the circled ones, it turns out that I got more money, right, 0.18, sorry, 1.8, but it could turn out that I could get less. So you're just comparing what did you do versus what would be the single best row of that things that adversary is filling up every round, okay. That's it. So that's the notion of regret, and so this kind of kills all the stochastic assumption that we're making, so Bernoulli rewards and all that. There's no such thing. And in this setting, it's still possible to design an algorithm which will have good worst case guarantee. Just like UCB was a slightly non-trivial algorithm but had some regret which was going like log of n, right? Similarly, here there's going to be an algorithm called Exp3, okay, some naming convention, Exp3, which will be an algorithm which will again have cumulative regret, which will be not going linearly with n, okay. It will be something sublinear in n. In fact, it will be square root of n, which we'll see in a slide, but that's the punchline. Basically, that there is an algorithm which doesn't need the stochastic assumption, will be able to deal with this objective, this type of regret, which is there's no expectations here. If there is expectation, that will be with respect to the internal randomness of the algorithm, okay. If the algorithm itself is flipping coin and doing something, then you need to take expectations with respect to that. And the Exp3 algorithm comes with a nice guarantee, same thing like UCB algorithm, okay. So what is the algorithm? The algorithm is as follows. So what it's going to do is it's going to maintain a distribution, a probability mass function over the k arms, okay. So think of me keeping a so where is this? Yeah. Or actually, let's assume that it just keeps a bunch of numbers for each arm, okay. So initially the numbers are ones for each of the arm, okay. Each arm there's one number and that number is 1, okay. These numbers are not the mean rewards, these numbers are not reward numbers themselves, but these numbers are just, I start with 1 1 1 1 for 5 arms. Next, what I'm going to do is for each time, now once I have these numbers, these are the numbers I'm going to keep from round to round. At each time, I'm going to pick an arm randomly, okay, according to 2 things. One is a ratio of these numbers. So for the ith arm, for the kth arm, I'm going to pick that arm with probability, that number divided by all the numbers, okay. In the starting point, it is 1 by k, right. That's because I had 1 1 1 for all of them, so 1 by k, or in 5 arms 1 by 5, okay. And just think of this multiplier as just adding some offset, okay. I don't want it's basically shrinking this ratio by a little bit. Let's say gamma is 0.1, okay. It's just like slightly reducing that number, this ratio, and adding some slight offset, okay. It's just for some correction purpose. It's actually not just for correction purpose. This is for what is called exploration, which we just discussed before, but let's not worry about the gamma parameter now. Once we know this probability of pulling that arm, I have this probability distribution, I can pull an arm. Okay, so that's it. So I'm gonna play that arm IT, and then all I have to tell you now is once I pull that arm, I'll get some reward. All I have to tell you is how do I update these numbers based on that reward. Okay, that completes the picture, right? So I'm maintaining, let's say in the 5 arm case, I'm maintaining 5 numbers. From those 5 numbers, I'm creating a probability mass function over these 5 arms that I will pull. I'll pull an arm, I'll get a feedback, right? And based on the feedback, I need to update these 5 numbers. Once I update these 5 numbers, I can go to the next round and again create this probability mass function, pull an arm, get some feedback, update these numbers. Okay, so updating numbers. So how do I update the numbers? I'm gonna, for the arm that I pull, okay, I'm gonna get some feedback x. Okay, let's call it x xs of k. K is the arm I pulled. So let's say I get a feedback xs. Okay, I'm going to divide it by the probability with which I pull that arm. Okay, so whatever the p number that I computed, it's a probability mass function. Okay, it's some sort of a correction factor. Okay, all I'm doing is whatever reward I got, I'm dividing it by the probability that I pull that arm. Okay, it's some correction factor to ensure some expectation or some averaging works. Okay, let's not worry about it. Some correction factor. But once I get that corrected reward, I'm just going to do the following, which is Wt at k is nothing but Wt at k, so Wt minus 1 of k. Oh man, I'm not writing it nicely. So Wt minus 1 of k, okay, times e to the power some constant times that x tilde. Okay, that's all it is. It's an iterative update. All it's saying is, I mean, the way I've written it here, it looks like there's a huge summation going on. All it's saying is whatever the previous number I was maintaining, multiply it with e to the power eta times the reward that I got. Okay, basically scale up the number if I got a reward. Basically, that's kind of, you know, if I get a lot of reward from that arm, I should scale up that number so that that arm is pulled more, and therefore I get more reward. Okay, that's the intuition. Okay, and that's it. So there are a few parameters. So what is this correction? The correction is to ensure the same thing like epsilon greedy, right? So you want to ensure that at least the arms which have like the worst weights, W numbers, are still at least picked up with some probability. Okay, so this correction number, even if this W for that guy almost is like, you know, is not changing, it's always 1. Okay, it never got upweighted, you know, then it's almost 1 by a huge number, so it's going to be kind of killed. So that means that I still want to kind of pull that arm, so that's it as an additive factor there. That's all. Okay, so this is called Exp4 algorithm. Okay, this is called also a randomized algorithm because inside, so the algorithm is behaving randomly. It's maintaining a distribution and picking an arm at random. Okay, just like Thompson sampling. Okay, the algorithm is randomized, and for this algorithm, people have shown that cumulative regret, the version that I showed ago, there's no expectations and stuff. Okay, if there is expectation, that's going to be expectation with respect to the randomness of the algorithm. Cumulative regret grows as only square root of n, which means that on average regret or instantaneous regret after a lot of rounds is as good as 0. So square root of n divided by n is almost 1 by root n. When n is really large, it's almost 0. So after a lot of rounds, you are doing as good as the best arm in hindsight. That I star, you know, what is the single row which would have fetched me the most rewards, you would at least do as good as that. Okay, so that's the key result here. So without any stochasticity, even if the underlying thing is stochastic, it doesn't matter, but the algorithm doesn't care whether things are stochastic or not. So the same algorithm can be used in the previous settings, but it has a slightly worse guarantee, square root of n, versus the previous algorithms which exploited the stochasticity to say I have a guarantee of log n. Okay, that's the difference. So that's Exp3, and let's not worry about this. So any questions about Exp3 and Thompson sampling? Yes. Oh, it's for exploration. So this is so that, remember, if I'm maintaining a weight for, let's say, the first arm 1, and that arm was never pulled, Okay, it just turned out that for like the next 100 rounds just happened that because I'm pulling things randomly, it was never pulled. Then the weight for that guy will always be 1, right? Or maybe it was pulled but I did not get any reward of 0. Then e to the power 0 is 1, so the weight never changed. Okay, whereas other guys were pulled, their weights increased maybe because maybe they got positive reward. So if because of weight of 1 after 100 rounds, the first term is going to be 1 divided by some huge number. These numbers w's are kind of increasing, right? They're getting multiplied by positive things greater than or equal to 1. So the first term will be still small, whereas you still want to do exploration. Maybe this first term is unlucky that it did not produce any reward. Then you want to still try it. So that's why I'm giving a constant offset of with some probability try that arm. So all arms get this constant probability of offset. So no arm is like never pulled. Okay, no arms probability is always close to 0. So they are always slightly above 0. It's like giving a probability of pulling the arm to be at least, let's say 0.1 or 0.05 or something. That's the offset. What's the time? Okay. So we were doing all this so that we wanted to learn and earn, right? So we said just estimating numbers is not good enough because I'm going to lose money. So I want to earn money, earn rewards, and estimate numbers. And I'm going to do that in a closed loop fashion where I try something and I get immediate feedback and I update my estimates and move forward, right? But the estimation here is very simple. I'm just keeping empirical statistics, for example, in Thompson sampling and UCB case, I'm just keeping average rewards, right? So average of the numbers that I saw. Okay. What we'll see next is the introduction of features, because that's where our supervised learning was features to prediction, not just a prediction directly, right? Without looking at the feature. So what we're going to do is figure out an algorithm which will be very similar to Exp3, which is going to go from a feature to an action. Okay, so it's a user feature dependent or a context dependent action. Okay, so that's going to be the slight addition. So what's the example? This was the original example we started with. Actually, users arrive with the feature, browsing history, accounts, user, their account information, previous visits, and so on. So we did not look at this when we talked about A/B testing, UCB1, all the epsilon gradient, all that. So we kind of ignored the features. We just want to take a decision, and there was a reward for the decision. We just want to figure out which decision is the best while learning and earning. Okay, here there's features. Okay, we do want to use the features. Okay, so how do we do that? Yeah, so previous methods are not enough because there is no context, but we still maintain this assumption that there is no carryover effect from one interaction to the other. So user comes with their feature. I show some page with maybe all sports. Maybe they don't click anything. That's the reward I got. In the next round, some other user comes with their own new profile. Okay, the way they behave has nothing to do with how the previous user behaved. Okay, it's just like the stock market. I bet on the stock market with Tesla. I'm not a billionaire, so it doesn't matter. Okay, but if a billionaire bets, there's going to be a change in the markets. Okay, that's the intuition. But if there's going to be change, that's going to be the subject of next lecture. Okay, so what do we get? So we get context, and we want to figure out the best action given that context or the user feature. Okay, best action, not just label. Supervised learning was about given the feature, just label it properly. Here, given the context, what's the best decision you want to make? Okay, the decision is richer than a label. Okay, so that mapping, just like in supervised learning, there's a function which goes from features to a label. There's going to be an object which is a function which we'll call policy, which goes from context to action. Okay, policy is nothing but something which goes from context to action. Okay, but the problem is we may not see the same context twice. So same user settings, so same profile, same number of visits, same browser data, you may not see. Okay, so you'll have to do something clever, right? If you are seeing the same context again and again, then you can just do Bandit. For the same context, I see it again and again. I'll try to do UCB1 or any of the epsilon gradient and figure out what is the best thing to show for that context. But you can't do that because context, first of all, don't repeat. And even if they repeat, they may not repeat like for 100 times, 1,000 times. that you expect. Okay, so let's see what we can do. Okay, so let's say we have 5 ads. Okay, again I'm talking about ad setting, but let's say we have 5 ads. So ads are things that I want to show. Those are my decisions. Okay, so A1 to A5. Like the first ad is by pet lizards. Okay, and let's say we also limit the number of policies we have. There are only 4 policies. Remember what I said? Policies were mappings from user profile to actions. So there are only 4 policies, which means that policy 1 says, okay, for these types of contexts, go to these ads. Policy 2 says, for the same type of context, go to some other type of ads. Okay, that's all. There are only 4 of them. In general, there could be lot of them, but let's say there are only 4 of them. Okay. Now let's look at, let's say if we apply, so let's not worry about policies, and let's say if we want to apply Exp3 directly. Okay. Okay, so actually let's look at policies, but let's think of policies as arms now. Okay. So we have 4 policies. We got a context. We have 4 arms. Okay, which is 1 arm per policy. And let's try to use Exp3 at the policy level. Okay, so instead of the action level, let's use Exp3 at the policy level. Okay, how does it affect? So let's say in round T, each of the policy says the following. The first policy says choose action A2. Okay, second policy also says A2. Third policy says A4. Fourth policy says A4. That's what the policies are saying. I have not yet picked any action arm yet. Maybe I pick one of the arms now using Exp3. I can maintain 4 numbers, right? 4 numbers per 1 number per policy, like same W1, W2, W3, W4, and now I choose arm E1. Okay, so I choose arm E1 as the first arm. Okay, by sampling from the weights, same thing as Exp3. Okay, and then therefore, since I picked that policy, the policy was saying show ad A2, which is 1/800 petunias, and you showed that ad. That's a decision, and then somebody clicked on that ad. Okay, that's great. Okay, the ad was clicked. Now Exp3, what it does is it just scales the reward that it got for that policy, right? So it has to update that number for that policy, for the policy that I use. So it just whatever reward I got, it was clicked and divided by the probability of picking that policy. Okay, that's what Exp3 does. And the rest of the arms, there is nothing, no reward, right? Because I did not even pick those arms. So reward is 0, and so the weights, the numbers are not updated. Okay. And the question is, and the idea is going to be that we can actually do better. Why? Because there are 2 policies which both recommended A2 and actually played A2. As in, ultimately I showed an ad A2. There were 2 policies which did that. Even anyway, through Exp3 I picked E1 and therefore it showed ad A2. But there were some other policies which also showed A2. Add A2. So what I'm going to do is we should be able to better estimate rewards for the policies which also said add A2. Okay, so there's the feedback is being transferred to multiple policies. Okay, not just the policy that I picked, but other policies which also said the same thing. Okay, so that's how I'm learning across policies. Okay, so that's the key idea, that I have policies, multiple policies can say the same decision. If I maintain weights on policies, okay, and pick one of the policies as to pick the ad, then once some ad is some feedback I get for the ad, whichever policy is predicting the same ad, that ad's performance, whatever feedback I got, clicked or not clicked, should influence the updating of the weights of all these policies which predicted the same ad. Okay, so that's the way I'm going to run the algorithm, and that's how I'm going to use the context. So policies are already predetermined, so they are mapping from context to ads. Okay, maybe I learned them, or maybe they are just finite number of policies. That's fine. So now I'm just updating the weights across policies. I'm going to focus on those policies which are doing really well. Okay, because the weights on those policies will be higher than the weights on the policies which are doing bad. Okay, that's the idea anyway in Exp3, as well as the idea that I'm mentioning here. And this idea is called Exp4. Natural, just to increment one number, but the algorithm, all it's saying is it's now maintaining weights on policies. Okay, so policy, I a policy, remember, is a mapping from features to action. I'm representing it as little pi, okay, little pi function. So there is a capital Pi number of them. For example, just think of pi 1, pi 2, pi 3, and pi 4 in the previous example. Okay, and in each round, I'm saying observe some context. Okay, and now you get a distribution over actions. Okay, I said distribution over policies, but once you get distribution over policies, you can also get a distribution over actions by just summing over all policies which are predicting the same action. Okay, so if I have 5 actions and 4 policies, I had weights on each policy, so I can get a distribution of policies anyway. Some numbers P1, P2, P3, P4. I can also get a distribution on actions. For example, probability of action A is the probability that did any of the policies predict action A for this context. Okay, I can add those probabilities. Okay, so that's PT of A. Okay, and that's it. This is the only change. Otherwise, you're maintaining weights. And the usual trick that I mentioned, there was a gamma by k or something, some additional factor. Sorry, there was an additional factor here, right? So remember, there was a slight correction where I was ensuring that none of the probabilities are too low, going to 0. So that correction factor, and that's it. And then you play. Don't worry about what this particular number is. That's not very critical. It's a specification of the algorithm, but it's critical for its analysis, the worst case bound, but not very critical in this explanation sense. Then you play action according to PT, okay, and you observe a reward RT. And now what are you supposed to do? You're supposed to update all the weights on the policies which all predicted the same action. Okay. What is it? K?
So in the first term you have 1 minus k times p of n.
Yeah.
And shouldn't be k times p of n.
Oh, the k is to ensure that there's a p mean being added to all the k actions or k adds. So let's say k is 5 here, 5 adds. There's the same offset, k, 0.1 being added to all the 5. So 0.1 times 5 is the total mass that was, you need to subtract that k times p min and then scale the previous numbers with that. Okay, it's just so that everything sums to 1. Okay, so you're asking why there's a k here and no k here. It's just so that everything sums to 1. You can check it offline. Okay. So yeah, that's the update. As I said, is basically for each policy that predicted that action, update with e to the power r by p. The reward that you got divided by the p. There's a multiplier of p min, but that's not very critical. That's just like some multiplication factor. Okay, it's just a constant. Just think of p min as some constant that's predetermined and doesn't matter. Okay, but the most important thing is that weights are being updated. So I'm maintaining weights on policies. Those weights are getting updated if the policies are performing well. In the sense, if the reward is not 0, then the weights gets updated. So those policies are now more likely to be used in the future. And this algorithm also has a nice regret guarantee. Okay, it's sublinear in the number of rounds. Okay, that's the key aspect. So any questions about this algorithm? Yeah.
So if we have multiple policies doing the same action,
yeah,
are we not spending a lot of time on computing all these and updating the weights there? Can't we merge them? What is
no, they could be same for some actions, but the reason why the policies are different is there must be some context in which they're saying some different action.
Okay, so there is some difference.
Of course, there has to be some difference. Otherwise, they're the same policies. If in every context two policies are saying the same actions, then they're the same policy. Okay, so when I said 4 policies, I mean they should differ at some place, so where they're at least saying for this context do something else. Okay, that's why I'm differentiating the policies. Yeah, but your point is correct that here I'm maintaining weights of policies, and the policies could be too many. And there are too many weights to be updated. Not too many weights to be updated, but too many weights to be kept. Okay, that's an issue which is actually true for Exp4. So Exp4 is somewhat computationally inefficient in that sense. Okay. So just as okay, I don't know if I want to do that computation. No, I don't want to. Like the policies could be too many. Okay, and we'll come back to this point maybe in the next lecture when we talk about reinforcement learning, because reinforcement learning will also have something called will have policies, because they also map from context to actions or states to actions. And so that should be a central part of next lecture. So we'll discuss that issue, computational issue, next time. Any questions about Exp4? Exp4 is like one level above Exp3. If you understand Exp3, then Exp4 is fine. And Exp3 and Exp4 were in the no probabilistic assumption setting, or basically it's also called the adversarial setting. Okay. Unlike UCB and Thompson sampling and epsilon greedy, which were in the probabilistic setting, as in you assume that there's a distribution or rewards for each action or decision. So now what I want to do is for the next 1 minute or 2 minutes, I want to just show a pictorial diagram of what, placing these algorithms, right? The first version is multi-armed Bandit, okay, where for each action there's a reward, right? Each action there's a reward. It could be stochastic reward, or it could be adversarial reward, in which case we saw Exp3, okay. But for each action there's some reward, okay. But other than that, there is actually no relation to the next action and the next reward. So there is an action reward pair in the current round, has nothing to do with the action reward pair in the next round. In the sense, if I take some other action or the same action, I'll get some other reward, but that has nothing to do with what reward I got in the previous round. Okay. Now, contextual bandits is also very similar, but there's also this notion of state or context. Okay. So both the policy pi is a mapping from state to action. Once you take that action, you get a reward. Okay. That reward can actually depend on both the context and what action you took, right? For example, if somebody is like a sports fan, that's the context, and your action is actually sports, then sports and the context together will give a very high reward. That person may click or engage with that web page a lot, right? So both the context and the action that you took together influence the reward potentially, or this edge is optional. I mean, but in general, both context and the action that you took influence what reward you get. That's kind of obvious, right? I mean, if somebody is interested in music and you show a sports page, sports action and the music context will give you less reward potentially, right? That's fine. But at the same time, again, there is no relation between context, action, reward in one round versus the context, action, reward in another round. Because the next round, some other context can come. In the first instance, some guy who's a sports fan will come. In the next round, there's somebody else who's like a music fan may come. They have nothing to do with each other. Okay, and therefore the rewards have nothing to do with each other. Now, what we'll study next class onwards is the fact that the action that you take has influence on what's going to happen in the next round, what's the context that's going to appear in the next round. Okay, so maybe you kind of you're in customer service, you really did bad customer service for the current user. The current user will go put out bad reviews on websites, and so the next customer you're going to come is going to be influenced by those reviews. Okay, so that's what I mean by there's going to be context which is going to be influenced by actions that you took in the previous round, okay, or previous rounds. Okay, so that's the non-triviality, and also the action that you take may not fetch you an immediate reward. Okay, so you maybe you did something like you decorated your store. Okay, that may not immediately get you like a high sales in the first week. Okay, but that has a long-term effect. There's some sales in the first week. Maybe it'll pick up because of decoration or whatever, cleanliness and something like that in your store. There's a long-term reward of that action that you took in the current round. Okay, so the two non-trivialities here are that the action that you take has influence on next contexts which come, and the action that you take has influence on the reward for that action can come to you several rounds down the line. Okay, whereas in the previous two settings, the rewards come immediately. The action that I took today, immediately there's